You know, for decades, computing had this one simple, beautiful promise. Just wait a year and everything you do will be faster, for free. But that promise? It's broken. Today, we're going to explore what happened and the two fascinatingly different paths we're now taking to solve the new grand challenge. How in the world do we command the massively powerful AI systems we've built in its place? Okay, let's dive right in.
For the longest time, we got what was basically free performance. Seriously, every new generation of CPUs just ran faster, so our software just accelerated. We didn't have to lift a finger. But as this quote points out, that whole era just vanished around the early 2000s. And it wasn't because we stopped innovating, it's because we ran smack into a wall of physics.
And this timeline really lays it all out. Through the 80s and 90s, it was a party. Clock speeds just kept going up and up. But then we hit that hard limit. Pushing the clocks any faster was generating way too much heat and sucking down too much power. It just wasn't sustainable. So the solution? Stop trying to build one single faster brain and instead build chips with lots and lots of brains. And that, right there, forced a huge shift to multi-core CPUs. And even more importantly for AI, the rise of the massively parallel GPU.
And this is where things get really interesting, because it led to this huge philosophical split in how we design chips. On one side, you've got the CPUs. Their whole goal was to basically pretend that nothing had changed. They added tons of complexity, these huge caches, fancy prediction algorithms, all of it designed to hide the fact that the chip was often just sitting around waiting for data. But GPUs, they took the complete opposite approach. They embraced the chaos. They basically said, waiting is fine. We'll just line up so much work that when one task is waiting, 1,000 others are ready to go.
And that brings us right to the core of the problem today. We've built these incredible parallel engines. But an engine is totally useless if you don't have a steering wheel. The new bottleneck isn't raw power anymore. It's how we safely and efficiently command these things to do what we want. So how are we supposed to solve that? Well, it turns out there are two major schools of thought emerging.
The first philosophy is all about teaching the machine to act like a really, really good human assistant. So instead of us changing how we talk, we train the AI to be a better listener and a much more reliable operator of the tools we already have. You can think of it as building the perfect apprentice.
This whole concept has a name, of course. It's called agentic AI. The goal here is to create a system that doesn't just give you an answer, but can actually do things. It can use a command line, it can run software, and it can pull off some pretty complex goals, all just from listening to our requests in plain English. The huge challenge, as you can imagine, is teaching it to use those powerful tools without making a colossal mess.
NVIDIA has this really clever three-step workflow to do just that. First, they solve the not enough data problem. See, most new software doesn't have thousands of examples to learn from. So they use something called synthetic data generation to spin up a huge high-quality data set from just a few starting examples. Next, they use a special kind of training to teach the AI what a correct command actually looks like. And finally, and this is so important, nothing, and I mean nothing, ever runs without a human giving the final thumbs up.
The secret sauce here is this system they call RLVR. Now, instead of asking a person, hey, does this look right, which can be slow and subjective, they just ask a piece of code, is this command valid? Yes or no? The AI gets a +1 for a perfect command, a -1 for a mistake, and a 0 if it's kind of wishy-washy. And this is just brilliant because it's deterministic. The same error always gets punished in exactly the same way, which makes the whole training process incredibly stable and way more efficient. And that brings us to the final, critical layer of safety. When the AI finally suggests a command, it's executed with this little flag, shell equals false. Now that might look super technical, but what it means is simple and powerful. The command is treated like a shopping list, not a recipe. This simple switch makes a whole class of really nasty cyber attacks known as command injection completely impossible. The human is always, always in control. Okay, so that's the first approach. Teach the AI to handle our messy human way of doing things, but wrap it in some very strong safety rails. The second philosophy asks a totally different question. What if we did the exact opposite? What if, instead of teaching the AI to understand us, we invented a brand new language that was perfect for machines from day one?
This is the big idea behind a system called the Universal Command Protocol, or UCP. The whole premise is that our natural language is just messy. It's ambiguous, it's expensive for an AI to process, and it's super prone to errors. So why are we forcing our most powerful computers to guess what we mean over and over again? Why not create a language that gets rid of all that guesswork?
So here's how it works. Your natural language prompt, something like start the server, doesn't go directly to some big, expensive AI brain. Nope. First, it goes through this lightweight little pipeline. It gets parsed, it gets standardized, and then it gets encoded into this super compressed machine-native format. All the messy interpretation work happens only one time, right at the very beginning.
And what you get at the end is this, a tiny self-contained packet of information called a UCP payload. Because it's so small and so standardized, it's incredibly versatile. Yeah, you can send it over an API, but you could also stick it in a QR code for an offline device, or just file it away in a log. It's basically a universal shipping container for a command.
So to put a formal definition on it, UCP is a protocol that's trying to be the perfect language for commands. The whole point is to completely cut out the ongoing cost and the potential for mistakes that comes from making an AI guess what you mean every single time. It is all about precision, efficiency, and clarity.
So that all sounds pretty cool in theory, right? But what does this actually get you in the real world? Well, the payoff is huge, and it really boils down to three things: incredible efficiency, rock-solid security, and the ability to scale up to massive levels.
Let's start with efficiency, and the number here is just kind of mind-blowing. The UCP system is targeting a 99% reduction in the number of tokens, the basic units of data and AI processes that you need to send a command, compared to just sending the raw text. Let that sink in, 99%.
And that massive token saving isn't just some abstract number on a spreadsheet, right? It has real physical consequences. Fewer tokens to process means less computation, which means less energy being gobbled up by those power-hungry GPUs for every single request. For any company running AI at scale, that translates directly into a massive drop in their energy bills.
But it's not just about saving money. The system is designed for speed and safety, from the ground up. On the one hand, there's a smart caching system, which means if the system sees the exact same command twice, it can just return the answer instantly. And on the other hand, every single command packet can be cryptographically signed. This gives you a rock-solid guarantee that the command is authentic and hasn't been messed with.
And to top it all off, this whole thing is built to grow. We're not talking about some little proof of concept here. The architecture is designed to scale horizontally. You can just keep adding more computers behind a load balancer, all sharing a central cache, to handle basically any volume of commands you can throw at it. It's ready for the enterprise from day one.
All right, so we've just walked through two really different, really powerful philosophies for commanding AI. One builds a better apprentice, the other invents a better language. So, what does this actually mean for the future? Let's just quickly recap these two big ideas. You've got the perfect apprentice approach, championed by NVIDIA, which is all about teaching AI to use our existing tools more safely. It's like a master craft person training an apprentice. Then you have the perfect language approach, like UCP, which is focused on inventing a fundamentally better way for machines to talk to each other. That's more like an engineer designing a universal standard, like USB or Wi-Fi.
But here's a thought. What if this isn't an either-or choice? Maybe the goal isn't to pick a winner. Perhaps the most powerful future is one where these two ideas actually merge. Just imagine, an AI agent, trained with all the safety and nuance of the perfect apprentice method, but it learns to communicate using the hyper-efficient and secure perfect language. That could truly be the best of both worlds.
And that really leaves us with one last big question to chew on. As we build out this next generation of computing, what's the real endgame here? Are we trying to bend these incredibly powerful, logical machines to our messy, ambiguous human way of thinking? Or is the real breakthrough when we finally learn to meet them in the middle, and we become more structured and more precise in how we command them? The answer to that is probably going to define the next few decades of technology.